So my thanks to you to joining my monologue, my last lecture on chapter 8 regarding interference effects. And of course, the title here today of this lecture will be Fabry-Perot spectroscopy. And I guess I should start my lecture by just pointing out that this title of my lecture is very, very badly chosen. I'm not as such speaking that much about spectroscopy, but rather I'm speaking about the spectral properties that are associated with Fabry-Perot instruments. So essentially interferometers and ethalons made using Fabry-Perot structures. So essentially structures where light is bouncing back and forth many times between two highly reflecting surfaces. That can be either mirrors or it can be just a single thin film structure, as can be realized using ethalons. So we're interested in learning more about the spectral properties of Fabry-Perot resonators, and we will learn about the limitations of these Fabry-Perot structures. Essentially, we will learn something about a free spectral range of such components that tells us of how broad of a wavelength range we can measure, or frequency range we can measure uniquely and unambiguously with these devices. And we will also learn parameters to quantify what is the spectral resolution of these kind of devices based on Fabry-Perot resonances. So essentially how narrow of a frequency distributions we can measure, or how narrow of a two different frequencies we can distinguish from each other. So these will be the things that we will be crossing during this lecture, and I will now start my journey. So, okay, let's start by motivating. So we have Fabry-Perot structures, essentially interferometers, and as we know, we can use them to measure quite narrow transmittance peaks. So essentially, when light is bouncing back and forth in Fabry-Perot structures, as we have encountered in the previous few lectures, what gets out is that we can write the irradiance of the transmitted light, and we know that it resembles an area function, so that essentially we will have peaks forming into the transmittance function of my device, and depending on the reflectivities of the mirrors or the interfaces, these peaks can be narrow or broad. And this is essentially what gives rise to possibilities that we could use these kind of components to do something related with spectroscopy. And here, okay, spectroscopic applications, we should think of this more broadly. So not just a spectroscopy as a chemist would understand, but rather we should understand the things where we want to, for example, look into different frequency components, or we want to, for example, stabilize a laser or some component into a very specific frequency. So with spectroscopic applications, I also mean that kind of possibilities. So for example, if I want to stabilize my laser source, a narrow band laser source, so basically a monochromatic laser, into a very specific frequency, then I could do this kind of stabilization basically by just using Fabry-Perot structures. And depending on the kind of accuracy or precision I need, either an ethalon would be fine, or maybe I would need a Fabry-Perot interferometer to do the job. But in any case, like, I would be able to stabilize a laser system. And the trouble here is that in some applications, we really need stable light sources so that their frequency actually is being locked into a very specific frequencies, and that we would actually know the frequency very accurately, so that we would actually know what we are measuring. And this is not a trivial task in reality when we are doing real engineering things regarding optics and photonics. And this is something that we are using quite a bit of these Fabry-Perot structures. So for example, like laser stabilization, it's actually a very big thing. And you should be kind of noted of the fact that we are not just speaking of spectroscopy here as a potential application, but rather like everything involving different frequencies. So that also involves, for example, stabilization of light sources, such as lasers. So basically what we mean here, broadly speaking, is that we are able to measure something that depends on the wavelength, so lambda, and we are able to change things And since lambda is associated, it's related to the frequency by the common formula that the frequency nu or f equals the speed of light divided by the speed of, wavelength of light in vacuum lambda, so that we know that either way we can measure something, how some parameters depend on the wavelength or the frequency, just a matter of taste. Similarly, well, we could also think that since these parameters we have used to describe irradiance distribution depends on the refractive indices of materials, and we definitely know that the refractive indices are in principle dispersive, so that they depend on the wavelength. We could in principle extract information of materials and their dispersion, and that could be related to their properties. And we know that we could also even just measure the transmittance function as a function of wavelength, so this would be really something more like a spectroscopist would be maybe finding more interesting, so that we can really measure a spectrum of some given sample in principle with these devices. And what we can also do, and this is already what I wanted to point out to you as a very important application, is that we can also try to stabilize the operation wavelength of a given instrument. And this can be done, for example, using ethalons if you want to use a cheaper structure, or it can also be done using a Fabry-Perot resonator if you want to be really precise and accurate about it. And then we can really stabilize laser frequency, for example, to a given atomic line transition, that otherwise we would not be able to do that. So essentially, like lasers, all of them, they drift, so that they kind of operating conditions are not perfectly stable. There might be, for example, small changes in the temperature of the system, of the device. There might be some small fluctuations in the air inside the cavity that is forming the laser system, and these things might be adjusting things. Like, for example, the piezos making piezo motors, like adjusting the laser cavity. There might be small drift in them into the driving currents, and all kind of fluctuations actually are present. And at the end of the day, what that means is that our laser sources are never exactly keeping their operation at a single operation wavelength. And that can be really helped by using these devices. So these are some of the applications that comes to my mind, and I hope that you kind of can grasp at least one or two of these, that they make sense, so that you know what is the point of trying to understand what are these Fabry-Perot structures and interferometers. So let's now start actually going through the different parameters of interest here, and let's start considering the spectral properties of Fabry-Perot instruments. So essentially, what we are changing here, or one way of looking at it, is that we are changing the cavity length of an interferometer, and we're now interested in looking more into the details, that what the change in the cavity length, how it changes, for example, the peak frequency associated with the transmittance peak, and so forth. So we are looking at the phase difference delta as always during this chapter, and earlier we found that to be of a type that we have 4 pi divided by the speed of light, wavelength in vacuum lambda naught times the refractive index nt times d times cosine of theta t. And d in the case of a thin film structure was the thickness of my thin film structure, and in the case of an interferometer that would be the cavity length. And this can be written differently, so we can write this instead of wavelength, we can write this instead of using frequencies. So we then have an equality that we have 4 pi times frequency divided by the speed of light times the ntd times cosine theta t profile. And now we can simplify our math, so we can just write things using a parameter known as an effective length L, where we have where we have hidden these parameters here, that we can simplify things, that instead of using a term looking obscure like this, we are just calling this just an effective length. And now our treatment is more general. It suits other cavities as well, so it's not only related or restricted to thin film structures. And now we know that the transmittance peaks, so essentially the interference patterns emerging into our transmitted irradiance, they take place when the phase difference delta is an integer of 2 pi. And this is what we have known many times already and seen that to take place. And now when we are changing the effective length L, what we see is that essentially the resonance frequency nu m changes in my resonator. And this is the kind of key thing here to notice. So we can change the math or the equation here above. So we essentially look into this, and we are now looking at a specific frequency associated with the given order m here, so that we can write this then simply that this equals to the multiple of 2 pi. And now we can solve this with respect to the frequency nu m, so that the nu m is equal to m, the order of my interference times speed of light, divided by 2L, where L is the effective length. Or equally well, I could write the effective length as a function of m integer to be m times c divided by 2 and nu m, so the frequency of my resonance frequency of my cavity. Mth resonance frequency of my cavity. And now let's look how things would be adjusted. So let's look how this effective length of my interferometer, so my resonator, like how that changes the properties. So essentially what happens when we slightly adjust the effective length, and let's consider that we adjust it by an amount of delta L. And now the corresponding frequency shift, so how our measured irradiance distribution changes, like we can now calculate simply by just differentiating the equation for the frequency we just derived. So and we do that with respect to the effective length L. So this was the equation we just derived for the mth frequency, and then we just calculate this when we differentiate this with respect to L. So we can write this to be minus mc divided by 2L squared. So essentially like we have 1 over L here. So when we take the derivative of this with respect to L, of course, this is what we get out. So this is how things can be calculated. So the differential of nu m essentially is approximately the delta nu m. And in here, the dl, the differential of the effective length, is approximately the delta L. And now we can simplify our math. This is the sloppy physics way of doing things, that we can write that the change with respect to the frequency is of a form that we have minus mc divided by 2L squared. And this is essentially the nu m divided by L and times delta L. So now we just see how a small change in the effective length, delta L, results in a small change in the respective frequency, the resonance frequency. And this can be written differently also, that this would be a form nu m times the relative change in length of my L effective length here. So okay, like what we have here is that essentially like we have now some means to estimate that if we are adjusting, for example, the cavity length, then we are adjusting also the resonance frequency of my cavity. And then like I can see that it's even the absolute frequency that matters, that I should be careful of knowing also that what is the actual frequency of interest in order to estimate like how much the frequency will be then changed when we are changing the cavity length. Another way of looking at things would be, I guess, looking at this equation and seeing the inverse of L squared proportionality here. So we see that in fact, when we are changing the cavity length, we're actually changing this quite dramatically. So if we are increasing the cavity length, we are quite quickly also making this smaller, so that we see the inverse square proportionality here. So that these are actually quite interesting and important when we are thinking of actual applications, that how accurately or precisely we want to be able to measure some frequency differences, or how accurately we want to be monitoring things. Then it's actually the cavity length that matters a great deal into the precision and accuracy of our measurements. And this is now something that tells about the kind of small change in the frequency, in the resonance frequency, when we are changing the cavity length. But this has nothing to do in terms of telling us about the overall bandwidth of my device. So basically of how many or how broad of a span of a different frequencies I could measure or operate my device with. So this is something that we need to define a new parameter, and I will be doing this next. So essentially now we want to tackle a question that can we, for example, use the same device to measure something taking place at the given frequency, and let's say, for example, the second harmonic of that frequency, or in terms of wavelengths, can we use the same device to measure accurately changes in the wavelength around 500 nanometers, and can we also see changes around 600 nanometers, or are we rather limited of measuring things only nearby the 500 nanometers? So essentially, what is the bandwidth, the operation bandwidth of my device? There will be clarifying figures later on, but I just wanted to first try to explain by words what we are aiming to do here. So now let's look into looking at the effective length delta L that would give rise to a shift of a transmittance peak to be perfectly overlapping with an adjacent peak. So essentially, we want to look how much of a cavity length, the effective cavity length, we want to adjust so that the peak corresponding to an integer of m would actually overlap with the peak of m plus 1, or vice versa, m minus 1. And this we can directly calculate, of course, easily, we know the equations already, so that the corresponding change in the cavity length is essentially the lengths of Lm plus 1 and Lm. And this is essentially by just looking at the earlier slides equations. This is speed of light divided by 2 times the frequency. And then, of course, the corresponding frequency difference that is associated with this change in the cavity length is given by a simple similar looking formula, and this is also C times 2L, where essentially the new M is a MC times 2L, and then we are just placing here M and M plus 1, and then we are doing the calculation and see that this delta nu, the bandwidth, is actually inversely proportional to the length. So that if I have a longer cavity, essentially this delta nu becomes smaller in quantity, and that actually would mean that I may not be anymore able to use the device on a very different wavelengths or frequencies, but rather I will be limiting my operation of the device to a more narrower frequency range. So this frequency difference, essentially it limits the capabilities to uniquely, for example, distinguish between frequencies. So essentially it limits the operational bandwidth of my device. And in another way of saying this, like if I'm looking at the 2 different frequencies, nu1 and nu2, I can define a parameter that the delta nu FSR as in free spectral range, and this would be my C over 2L. So essentially this must be, and this is larger than the difference. This free spectral range is a parameter that must be larger than the separation of the frequencies nu2 and nu-m in order for me to uniquely distinguish these 2 frequencies. So essentially, I started by here looking at the 2 adjacent peaks, and I found a condition that how the cavity length adjusts, changes the frequency change or bandwidth, and now I'm defining this delta nu to be my free spectral range. And this is actually a very useful parameter in terms of understanding the operation of a cavity, because that really tells us about the bandwidth. So please memorize this. What is a free spectral range, and essentially how it relates to the kind of operational bandwidth of my instrument. So I will try to now clarify the meaning of the spectral range using a figure, like a graphical description is always good, an illustration, and now hopefully we can see better what we're aiming at. So when we are measuring frequencies, so we are, for example, measuring the peaks of a nu1m, and we would be then measuring a nu2, the second frequency of the of the even higher integer of a diffraction order. We see now that these 2 peaks can actually be mixed together in the case that the absolute difference between the frequencies is larger than the free spectral range that was equal to C over 2L. So what I mean here is that the free spectral range is essentially the difference between the adjacent resonance peaks of my resonator. And now if I have two frequencies that are different, so I have nu1 and nu2 here, and I can now distinguish them uniquely so that I can really know that what is the difference between the two frequencies as long as their absolute difference is within the free spectral range. But if the difference is actually larger, I may not anymore be sure that is the difference in frequency actually like just a difference, or is it some integer of m of frequency difference. So the trouble here is that how can we possibly in unique way distinguish the peaks, the frequencies from each other. And we cannot anymore distinguish them if their difference is larger than the free spectral range. So it boils down into this that we do not know is the frequency difference nu2 minus nu1, or is it, for example, m times nu2 minus nu1, or 2 times nu minus 1. And this is the trouble that we have, and this is ultimately limited by the free spectral range. And please note here we have the cavity length here inversely proportional to the free spectral range, so that it's really the cavity length that is a key parameter here that defines the operational bandwidth. So there's always a kind of compromise in performance. If you want to measure something very accurately, then you are limiting the bandwidth of your device, that you may not use it for measuring many different frequencies, but rather you're restricted in scope. And now finally, we will estimate or define parameters that can be used to estimate the performance of these kind of instruments in terms of their spectral resolution. So basically how small of a frequency differences we can measure with these instruments. And here I would warn you, and I will warn you, that there will be many different criteria out there in the literature to define what is the spectral resolution, or what is somehow defining this fact that we want to measure different frequencies and how accurately we can measure the different frequencies. So please be always sure that you know your terminology here. So here we use and introduce a few different criteria, different definitions how we can quantify the spectral resolution. So essentially we define the frequencies nu1 and nu2 to be distinguishable if the maxima of the subsequent peaks, the related peaks, are a distance of half with gamma value away from each other. So essentially, this is explained in here. So I'm defining that I can resolve these two peaks when they are a distance away that is half with gamma value distance apart. And this is how one way of defining things. So basically the delta, smallest change in the phase, corresponds to a 4 pi delta nu times c times L. And this essentially is approximately the gamma value here as we define things. And this is now approximately, for the case of having sharp peaks, 4 divided by the square root of the finesse coefficient. And here delta is basically the 4 pi nu divided by c times L, as we discovered in the first or second slide of this lecture. And now I can solve this with respect to the smallest possible frequency difference I can measure. So I'm basically solving this with respect to the nu min, this equation, and that gives me that the equation that is approximately c over L, the effective length of my cavity, times pi times the square root of finesse coefficient. And this is known in the literature as the spectral resolution. And this is, of course, like an absolute value. So it's giving really things in terms of, for example, a frequency, or if it would be describing things in terms of the wavelength, it would be given as a wavelength. And now another way of looking at it would be to define a spectral resolving power of the instrument. And this is a unitless value. So it's defined as a ratio, so that we are measuring a given frequency, nu m, and we are now calculating the ratio between the nu m and the smallest possible change we can measure. And now this is equal to m times pi of square root of fineness coefficient f divided by r. And this is now essentially m times the fineness of my cavity. And it's a ratio, so we know that it's a unitless parameter, so that it's a slightly different kind of term parameter to describe the behavior of my cavity. So it's not spectral resolution as defined in here, which has units. And of course, we can see the differences here, that this only depends on the cavity parameters, on the fineness. And in here, we can see that the spectral resolution also depends on the cavity length, so that there is a difference between these two different ways of quantifying what are the spectral properties of my cavity. So how finely, how accurately, precisely I can measure differences in the frequencies. So finer resolution, so basically when the delta nu min is small, then this corresponds to greater resolving power and greater fineness. So this would be the how we say things. So that when we are speaking about the better resolution, finer resolution, we just really mean that we are able to see more accurately smaller changes. So this is basically what it boils down to. And if you're measuring things using a cavity, basically it's the fineness of the cavity that dictates what is the resolution or resolving power of my instrument. So this is what I wanted to say during this lecture. I hope you got at least something out. This is actually a subtle thing when we are speaking about the spectral properties of Fabry-Perot structures, because I understand that it requires from you quite a bit of a grasp of applications in optics and photonics, so that you would really be able to put things into a proper concept. But I hope that the figures help you out a little bit, and at least the kind of good parameters to know would be the free spectral range, and kind of understand that there's always a compromise between the bandwidth of my device and in the actual kind of like a spectral resolution, that how accurately I can actually measure things. So this is something that you should at least understand and remember from this lecture. And here, this was the last lecture on regarding interference. So I hope you learned many useful things, and I want to congratulate you at the end of these lectures. You did well listening me and my monologue for a long while. So please have a restful rest of the week and enjoy the rest of the day or evening or night or morning whenever you're listening at this video. So thanks for your time and patience, and please join me shortly when we are actually starting our journey then towards the diffraction effects. And there, in a way, again, we'll be also just calculating superposition of fields exactly just like we did in this chapter, interference, but now rather than considering a discrete number of fields, we're actually considering a continuous distribution of fields. So that will be basically, in a nutshell, the only new thing we will be introducing. But more on that, of course, in the upcoming lectures regarding diffraction effects. So I thank you for your time, and please enjoy the rest of the week. Thanks, and bye-bye.